Okay, welcome to Chapter 7, Multivariable Calculus. The topic of multivariable calculus is massive. There's a lot to unpack there, but this is just an introductory course, so we're going to really just do some very limited things. And in particular, this section, 7.1, should be a nice, easy, simple section. Just an introduction to working with functions that have additional variables. In thinking about how to evaluate them and how to graph them is what we're going to do in this section. Okay, so in general, an equation of the form z equals to f of x comma y describes a function of two independent variables. If for each permissible ordered pair x comma y, there is one and only one value of z determined by the function f of x comma y, the variables x and y are independent variables, and the variable z is a dependent variable. The set of all ordered pairs of permissible values of x and y is the domain of the function, and the set of all corresponding values of f of x comma y is the range of the function. Unless otherwise stated, we will assume that the domain of a function specified by an equation of the form z equals to f of x comma y is the set of all ordered pairs of real numbers x comma y, such that f of x comma y is also a real number. Okay, so what is this saying? First of all, let's refresh our memories about function notation, independent variable, dependent variable, and how we kind of use that. And we'll come back and revisit this. So let's say, for example, a little math history here. Okay, so early on in our experience with algebra, we're introduced into equations that generally or often fit this kind of a form. Y equals to, say, 3x plus 2. So we just traditionally use the letters x and y. At this moment, there really isn't any conversation about inputs or domains or ranges, anything like that. But maybe you're asked to evaluate when x equals to, let's say it's equal to 4. And then maybe a separate one when x equals to -5, for instance. Okay, so you would take this function, right, and you do y equals to 3 times something plus 2. And for the first one, we're going to let x equal to 4, so we put a little 4 there. And then we can evaluate this. So we end up with y equals to 12 plus 2 makes it 14. So there you go. So when x equals to 4, y equals to 14. Right? On the other hand, we also have y equals to 3 times blank plus 2. So then for this one, we have -5. So -5 times 3 is -15, plus 2 is -13. So y equals to -13, right? So then we have a new statement here. When x equals -5, y equals to -13. Okay. Well, we have a similar thing when we have an additional variable now. Well, actually, I should say note that we could have more than one instance of the variable x. So we could have an equation like this: y equals to x plus 3 divided by x minus 2, for instance. But notice that this is just another copy of the same variable. And in fact, let's go ahead and make it squared, like that. So now evaluate when, x equals to 3. So if we do that, then we end up with y equals to, well, I don't want it to be confusing with that 3. Let's make it a different value. How about 5? And x equals to 5. Okay, so then we get y equals to blank plus 3 divided by blank minus 2, and then that whole thing gets squared. So we're going to put a 5 here and a 5 there. So we get 8 in the numerator, and the denominator is going to become 3 squared is 9. So we end up with y equals to 8 divided by 9. Okay, so when x equals to 5, y equals to 8 divided by 9. Okay, easy stuff, right? Then later on, they introduced function notation now. So now, instead of writing the equations this way, they introduce function notation. And so now we're going to let y equal to f of x. So we can rewrite this same equation here, can be restated in function notation as f of x equals to 3x plus 2. Right? So we adopt this new notation style. Same thing over here. We adopt the new notation style, and maybe just a little bit wider over here. Then this becomes f of x equals to x plus 3, and then x minus 2 squared. By now, you're very comfortable with function notation. But if I can remind you, I think almost everyone has a difficult time at first when you're first introduced into function notation. Maybe perhaps because the y kind of disappears once we state it like this, once it's given to you in function notation. There's really only the input variable x, right, the input variable, and the output variable is this value, right, as a function. F of x, this whole thing over here is the output, and it is our y. So this is a, this can get a little bit confusing when you first get introduced to this, but it allows, nicer notation, right? This then can be rewritten as f of 4 equals to 14. Makes it easy to tell that the input is 4, the output is 14. Likewise over here, this would be f of negative 5, f of negative 5 equals to negative 13. Good. And then one of the reasons why function notation is useful is because then you can label it different things, right? Instead of labeling this as f of x, I'm going to come back over here and rename it as g of x. That way there's no confusion between this function and that function. So here's a different function. So this statement down here can be rewritten as g of 5 equals to 8 over 9. Okay, obviously material you're very comfortable with. Okay, so now let's extend this to a function with 2 independent variables. Again, we often use the letters x and y, it's just customary. So if we have a function f of x comma y, this lets me know that there's going to be 2 different input values that are needed for me to evaluate an equation, and then the output value is the z, right? So just like before, this can also be written as z equals to some equation involving x and y. So it could just be like, say, 2x minus 3xy plus 5, let's say. Here's an equation. The input values, the independent variables, are x and y, and the output value is a z. And just like before with function notation, we can then restate this as the function x comma y equals to 2x minus 3xy plus 5. Okay. Paying attention to the order in which these independent variables are listed is important. Because when you're prompted to do something, you're going to be asked things like this, like evaluate f of 3 comma 2. Oh, that's a lot of 3's and 2's running around. Let me change that up. Evaluate at 4 comma 1. Okay, so now it's important to pay attention to the order because this states that the x must be the 4, right? So evaluate when x equals to 4 and y equals to 1. So the order is important. And now we come back over here, and so this would be 2 blank minus 3 times blank plus 5. And so this is going to be an x, so this is a 4, and this is a 4, and this is a 1. Good. So now we can just evaluate this. F of 4 comma 1 equals to 8 minus 12 plus 5. So 8 plus 5 is 13, minus 12 equals to 1. So f of 4 comma 1 equals to 1. Right? Pretty easy, I think. It's just evaluating equations. You just have to pay attention to the independent variables, the dependent variable, and I hope these kinds of questions shouldn't be a problem at all. Okay, so let's take a look at the examples from your homework. Let's see. So as you can see, some of the early questions, such as these here, a function is given using the variables x and y as independent variables, and they ask you to evaluate using these values over here. So like, for example, number 12 says go to the f function, that's this one up here, let x equal to 5, let y equal to 6, so replace the x with a 5, the y with a 6, and then evaluate. Pretty straightforward. Down here, same thing, except we have 3 independent variables, x, y, and z. So for number 20, for example, we want to come back to this complicated looking equation and replace the x with a negative 10, replace the y with a 4, and replace the z with a negative 3 in this statement, and then evaluate it. I feel like that should be pretty straightforward. Same thing with these, just evaluating. You know, those should be all pretty easy, I think. Right. Let's think about how to graph them, though. That might be a little bit trickier. Okay, a three-dimensional coordinate system is formed by 3 mutually perpendicular number lines intersecting at their origins. See figure 1, so that's this figure right below. In such a system, every ordered triplet of numbers, x, comma, y, comma, z, can be associated with a unique point. Okay, so this is what it would look like. We have an axis this way. Typically, we like to put the one that goes up and down as the z, and then we have these other two this way, or x and your y. So in order to plot a single point in this system, we need 3 values. So the input value of x, the input value y, and then the input value of z, right? Those 3 pieces of information lead to one individual point. So just like when we did it with 2 dimensions, right? Let's think about 2 dimensions. So just the way we graphed back with our 2-dimensional grid. So let's look at this dimensional grid. Typically we had the y-axis going up and down and the x-axis going left and right. So we might be asked to graph, the point 3, 5, right? And this would let us know that the x is a 3, so we got to travel from the origin. We travel 3 units along the direction of the x-axis. And then we got to travel in the direction of the y-axis by 5 units. That would get us to maybe this point up here. That's supposed to be a straight line. Let's pretend that's a straight line. And that leads us to our actual point, which is right there. Right? So this black part there is the path we took to get there, but it's not part of the graph, right? This represents just a single point. So once we get there, we would come back over here and erase the path to it and simply point out that that individual dot there is the point 3, 5. So likewise, when we're working with 3 dimensions, there's all these lines that lead to that point, but then we're supposed to ignore the path and just focus on the fact that that point there is the point that we're graphing. Right, so coming back over here, this just represents a single point in this 3-dimensional space. The path that we took to get there would then kind of be erased, right? So it's the rest of this blue is not part of it, just that dot, right? So for instance, if we wanted to graph the point, let's come back over here, about graph the point -3, 5, 2, right? So this lets me know that the x is a -3, the y is a 5, and the z equals to a 2. So looking at this kind of a grid, come this way, come this way, come that way. Assuming this is the x, y, and z. Okay, so in this direction, we're going to assume that this is the positive direction. So then going from here, this is 0, 0, 0. So this is like 1 there, and 2 there, and 3 there. So then going back that way is -1, and -2, and -3. There's -3. The y direction, again, we assume that going this way is positive, so that's going to be 1, 2, 3. And then back this way, in that direction, is negative, so this back there would be -1 and -2, and so on and so forth. The z, the up and down, okay, so go up, this value is a +1, +2, +3, so on and so forth. And then down this way would be the negatives. So down this way is -1 and -2, and so on and so forth. Okay, so let's put it in blue, -3 for x means that we go back this way. And then we travel 5 units in the y-axis direction. So we're going to travel this way until it goes 5 units. So let's say that this is 4 and this is 5. 4, 5. So this corresponds to this value right there. And then we're going to travel up in the z-axis direction by 2 units. So then this is going to come up this way, and it's going to be a height of 2 units. So 1, 2, matching with the height of this value here. And that will finally allow us to reach our destination, which is one solid point. Good. So this point right there would be the point, the triple pair, -3, 5, 2. And just like in the case when we had 2 variables, the blue path is then kind of forgotten, right? We kind of erase it. It's not part of the graph. Just that individual dot is the solution, right? That triple pair there corresponds to that little dot that's kind of floating in midair. All right, well, your author provided you with a better image of this. So let's take a look at that. So again, we start at the origin. This is 0, 0, 0, 0. X in this direction is positive, so that's +1, 2, 3, the x-axis direction, and -1, -2, -3. So right there is -3 in the x-axis direction. So then we travel 5 units in the y-axis direction. Right? So this corresponds to this. That's going to be a +1 there, a 2, a 3, a 4, a 5. So this corresponds to this guy on the XY plane, sort of the floor of this. And then finally, we travel 2 units in the z-axis direction. And this corresponds to this, where going up, in this image, going up is the positive direction. So this is going to be a 1 and a 2. So this matches with the height of that. Good. And so just like before with the 2-dimensionals, then the path that we took to get there is kind of ignored. We don't use it anymore. So we would kind of ignore it, and so this over here is no longer part of the picture. I think that confuses people sometimes. Right? The path that we took to get there is no longer important. It's just that there's a dot there. Good. All right, let's use technology. There's an online graphing tool that will let us graph three-dimensional graphs. So let's take a look at that. I found this 3D graphing grid, this one. You can go to this website right here if you want to play with it yourself. So we can have a better idea of what this looks like. We can kind of rotate this around and play with it. So we can see that we have the blue goes up and down. It's the z-axis. Here we have the x-axis in red, starting at 1, 2, 3, 4 positive direction, and then -1, -2 in the negative direction that way. And then we have y going this way. Rotate it. The y is the green. Oh. And so here it is in 1, 2, 3, 4, and then -1, -2, -3. Right? So you can rotate this around a little bit. Okay, so keeping track of which direction is positive and which one's negative. Okay, so if we wanted to graph the ordered pair, the triple pair, we had -3, 5, 2. There it is. And let's change the color. I'm not happy with that color. A red dot. No, let's make it that. It's fine. And there it is. So it's this point right there is the one that we're getting at. And if I just twist this around, you'll see that it's floating in midair. There it is. So that's a little easier to tell that it's a point floating in midair. This grayed out plane over here is the XY plane. Right, so we see that we've traveled -3 units in the x-axis direction, and then 5 units in the positive y-axis direction, so that would be that way. And then we travel 2 units up to get to that point right there. Okay, so that's just one point, but we can graph more points. So if we had, I don't know, about -2, 4, 3. Here's another point, point B. Right, so we can start to stack up lots of different points. And then as we see that there are equations that will connect two input values, right, x and y values. So it'd be 2 points sort of on this gray floor that come together. Every point on this grayed out plane is a point which is a x comma y. And then if you input that into an equation that depends on x comma y, you get one resulting z value. So there is 1 point that corresponds, one z value that corresponds to each x comma y input pair that will then result into a point that kind of floats somewhere. And then eventually those points might come together to form three-dimensional shapes. Okay, say that we're given this equation to work with. F of x comma y, and it's x squared minus y squared plus 2, right? And maybe they ask you to graph it. Well, just like in the one independent variable case, we need ordered pairs. We need to figure out relationships between input-output values. So if you don't have technology, the only thing you could do is just create a table, come up with values of x and y. Remember, these are independent values. And then you put them in your equation and find the corresponding output value, right? So we can begin by creating a table where we come up with an x value and a y value. So let's say x, this is an x comma y. So let's say, for example, 0 comma 0, right? So we're going to put in blank squared minus blank squared plus 2. I'm going to type in a 0 there and a 0 there. Well, that's just going to clearly lead to 2. So we have our first triple, 0, 0, 2. So this is 1 point in the graph of this function. Then we do another one, right? There's the independent variables, so we get to choose any and all of them. So how about -1, 2? All right, so blank squared minus blank squared plus 2 equals, so here we're going to put in a -2 there, and -1 there, and a +2 there. That's going to become 1 minus 4, that's going to be -3, plus 2 becomes -1. -1. So we have another ordered pair, -1, 2, -1. Right? And so the question that I often get is, well, how did you know this was the right thing to put in? And it's like, there isn't a right thing to put in. You got to put them all in, right? Just like in previous cases where we only had one independent variable. If I just had f of x equals to x squared minus 2, and I wanted to graph this, we would create a table, right? And then we'd have x values, and you got to input all and anything right in the domain. Ideally, it would be nice to create a nice variety of input values here so you can get a pretty good idea of what the shape is going to look like. But that's all we do, right? We just come up with different input values. How about if we put a 2 here and a -3 there? So this would be blank squared minus blank squared plus 2. And this time we have a 2 for the x and a -3 there. So that becomes 4 minus 9 gives you -5. -5 plus 2 equals to -3. So yet we have another triple pair. 2 minus 3 minus 3. Right? So if I graph these individual points, there are 3 dots, sort of in the air. Let's go back to our graphing tool over here. So let's graph these points. So if I graph the point 0, 0, 2, that's 1 point. And then if I graph the point -1, 2, -1, we get to a second point. No, that didn't work. Parentheses, -1, 2, -1. Looks better. 2 points. And then we go for a third point, about 2, -3, -3. That gives us 3 points. So at the moment, I have 3 dots in this grid. They are, right? 3 dots. Looks like only one of them is above the plane, the XY plane, up here, and then the other 2 are below that plane, right? Because these 2 end up being negative, so there's only 1 point above the XY plane. Okay, so 3 dots is just not enough to give us information about what the picture is going to look like, right? It's just not enough information. When we had a 2-dimensional grid, often we would start to see a pattern early on, and we can kind of guess what the whole picture is going to look like. But with 3-dimensional grids, it's just not enough information. This could really just be anything at this point, right? So we keep going. We come up with more dots and more dots and more dots, as many dots as are needed to eventually get a sense of what the graph looks like. And if you notice over here, I've already typed in the actual equation we're working with, x squared minus y squared plus 2. So if I just click on here, it'll just continue to graph more and more points until eventually an image is created. Right? And this is what that image is. This is what it looks like. Hard to twist it around a little bit more. Maybe zoom out a little bit. So those 3 blue dots are on the surface of this black shape. You can kind of see here that that dot is on there, and this dot is on there, and so is this one. Okay, so hopefully it's clear to see what this looks like, right? This surface. It's an interesting one. You get some very interesting three-dimensional grids as you rotate around and kind of see this from the top down kind of approach. It almost looks like a mountain range kind of thing. Notice that from certain angles it can look like a parabola, right? So from this angle we see that there's sort of this parabola here. And from this perspective, if you're kind of traveling along here, then it looks like this point right here is a minimum, right? You're coming down, and you hit the bottom, the valley here, and that's a minimum. On the other hand, if you're coming up from over here, from underneath, you're coming up, and you reach to a maximum there, and you come back down. So from a certain perspective, that point right there, maybe I should change its color. Or I should, let's change it to a red point. Yes. So this red point right there is an interesting point because from this angle, right, as you're coming up, this looks like a parabola, and it looks like a maximum there. It's the maximum value you can get from this direction. On the other hand, if you twist it around a little bit and come over here, now it looks like a parabola here. And so if you're coming down along this direction, it becomes a minimum, right? So that point is not a minimum or a maximum. It's just, it depends on the perspective that you're looking at. Good. So we call that a saddle point. That point right there. It's called a saddle point. Maybe from this slight askew angle, it's a little easier to see. Okay, well, you can very easily change this. Let's get rid of these dots on here. Remember, this whole black image here is a collection of an infinite number of dots that are, each dot is a triple pair that comes from this equation right here. But we can easily manipulate this equation and get completely different shapes. Notice that if all I do is come back over here and change this to a plus, the whole picture changes quite dramatically. Turns into that, right? So here is the image of that. And all I did is add a plus sign there. So let's think about a couple of easy points. So if x is 0, y is 0, then this would be 2. So 0, 0, 2 is still a point on here. There it is. Right? Let me zoom in a little bit more. There. You see that that point A is sort of the bottom of that little bowl there. Okay, let's get a couple more, a couple of easy ones. If I put a 1 there and a 1 there, then they get squared, so it'd be 1 squared plus 1 squared. That's just going to be 2, plus 2 is 4. So this could be a 1 there, a 1 there, and then that would result in a 4. So this should also be a point that's on there. What just happened? It said 1 there, 1 there, and 4 here. There, so there's a point that's on here. Let's find, there it is, point B, sitting right there. You can see it embedded in the center of that saucer shaped thing. Like a pimple on it. But let's a couple more easy ones. Well, in fact, because we're squaring them, really any combination of 1 or negative 1 will still give us the same answer, right? So if we can just easily just fill out a couple points here, I know that this is going to be an answer of 4 whenever the x and the y are any combination of 1s. So that should also be a point. 1, comma, negative 1, comma, 4. That's point C. Let's find it over here. There it is right there. And B, also the other way around, I could put a negative 1 there. That should also lead to 4. It's D. Where's D at? There's D. Right there. And you see how these points are all on the surface of this shape. Good. Another easy one would be, well, we could put a 0 for x and any other value for y. So we know 0 squared is always going to be 0. So then any other value we put over here would result in a value for y squared plus 2. So for instance, another easy point would be 0, comma, let's put in a 2. 2 squared is 4. 4, 2. 2 squared is 4 plus 2 is 6. So that would result in a 6. So there's another ordered pair that is easily on here. And let's change the color on this one. I just want to pop out a little bit more. Colors, I don't know, how about green. Okay, so there's that one, E. Good. Okay, so we get the point. This could be a good website for you guys to come in and type in some equations, get a chance to see a nice 3D grid, and hopefully get comfortable with it, right? So remember that there's always this XY plane on the floor here. I always refer to it as the floor. We come up with an XY value, and then we input it into our equation, and then that will lead to a point on the actual graph, the actual shape. All right, so this is pretty much all you need for your homework, I think. Okay, let's take a look at this example from your homework. Number 58, revenue, cost, and profit function. So a company manufactures 10 and 3-speed bicycles. The weekly demand and cost equations are given. So we have P equals to 230 minus 9x plus y. Q equals to 130 plus x minus 4y. And then we have a cost function of producing both bicycles, x comma y. So this is C of x comma y equals to 200 plus 80x plus 30y, where P is the price of the 10-speed bicycle, Q is the price of the 3-speed bicycle, X is the weekly demand for the 10-speed bicycle, and y is the weekly demand for the 3-speed bicycle, and C of x comma y is the cost function. So find the weekly revenue function, R of x comma y, find the weekly profit function, P of x comma y, and then finally evaluate R of 10 comma 15 and P of 10 comma 15. Okay, so we have the 10-speed bike, 10 speeder, and we have the 3-speeder. No, this 10 and this 3 are numbers that don't matter, right? They're just part of the label, the type. You know, this is bike type A, this is bike type B kind of deal. So don't let that confuse you. Okay, but then we have price, you know, what you charge for it, and then you have demand. Okay, so the price is P. P is the price of the 10-speeder, and Q is the price of the 3-speeder. Q is the price of 3-speeder. X is the weekly demand, demand by week. And so this is X is the weekly demand for the 10-speeder, and Y is the weekly demand, again, weekly demand, Okay, so then find the weekly revenue. Good, so they all match. Weekly demand, find the weekly revenue, find the weekly profit. Okay, so we don't have to do any kind of weird conversions there. Everything is in terms of weekly statements. Okay, so for revenue, we know that revenue is the total amount of money collected. So revenue of X, Y is going to be all the revenue from the 10 speeder, revenue from the 10 speeder, plus the revenue from the 3 speeder. Good. So the revenue for the 10 speeder is going to be equal to the price, P, times the demand, which is X. That looks like function notation here. Let me restate that. P times X plus, and then the revenue for the 3 speeder, well, that's the price that you charge times the number of units sold, right, on the weekly basis. Price times demand. Price times demand. Okay, but the P is equal to this equation up here, and the Q is equal to this equation up here. So then we take this statement here, and we say that the P was 230 minus 9x plus y, and we multiply that by x, plus the Q, which is 130 plus x minus 4y, and we multiply that by y. So here is our revenue in terms of x comma y. We've technically finished. This is the right answer, but we do need to simplify it. So now that we wrote down this statement, let's distribute this x. We end up with 230x minus 9x squared plus yx, plus, now distributing the y, we get 130y plus xy minus 4y squared. And so finally, if we try and combine like terms, there really isn't too much in common, right? Now, the order in which we multiply does not matter. So we have an x times a y there, and x times a y there. Those will combine. And that is unfortunately it. Nothing else will combine. So let's rewrite this from descending order. Minus 9x squared minus 4y squared. Took care of this guy. Took care of that guy. Then there's 2 copies of xy, so I'll just put plus 2. Yx or xy, that doesn't matter. The order doesn't matter. So there's 2 of those. And then there's a plus 230x plus 130y. So here is our revenue function, x comma y. Give me the value of x and the value of y. We input it into this crazy equation, and the output would be the revenue, the weekly revenue generated when demand for the 10 speeder and the 3 speeder are given with the values of x comma y. Okay, that takes care of the first part of the question. Also find the weekly profit function P of xy. Remember, profit is equal to the revenue minus the cost. So all we have to do is take this revenue function and subtract off the cost function. Let's come back up here and say that this is going to be equal to profit is equal to revenue minus cost. So for us, P of x comma y is going to be equal to this crazy long thing, minus 9x squared minus 4y squared plus 2xy or yx plus 230x plus 130y. And then from that, we're going to subtract off the cost function. So minus, I'm just going to squeeze it underneath here a little bit, minus 200 plus 80x plus 30y. Okay, so there's our answer. But we have to be careful because this subtraction applies to the entire thing. So I'm going to put parentheses there. So I'd be sure to distribute. And then combine like terms. So my profit, P comma Y, is going to be equal to, well, nobody wants to play with this guy at all. So it's going to be minus 9x squared minus 4y squared plus 2xy. And then minus 80x will combine with that, or simplify with that, reduce with that, to give us 150x. So plus 150x, put it underneath here, plus 150x. And then minus 30 here gives us plus 100y. And then there's this minus 200. Oops, that takes care of everything. And there's our profit equation. Good. Finally, they ask us to evaluate r of 10, 15. So r of 10 comma 15 is equal to minus 9, putting a 10 in there, squared, minus 4 times blank squared, plus 2 times blank blank plus 230 times blank plus 130 times blank. So if the 10, oh, let's put it in color here. So let's make this a 10. So if the x is a 10, then this is a 10 there, and this is a 10 there, and this is a 10 there. And let's put the 15 in green. So this would be a 15 there, a 15 there, and a 15 there. Good. So the rest is just a little bit of arithmetic to figure this out. Obviously use technology. And let's come back over here. For this guy, P of the same thing, two values, is going to be using this equation. Minus n So if we let x equal to 10, there, 10, 10 over there, and then 150 times 10. Okay. And then y was 15, put a 15 there, 15 there, 15 there, and a 15 there. And again, now you can just use technology to figure them out. Okay, so then we can come to our trusty calculator over here and evaluate these. So let's put this, that. Okay, so it's negative 9 times 10 squared. Enter. Okay, so 2750 is this one. So r of 10 comma 15 is 2750. Good. And then that's the revenue collected. Now let's look at the profit. Right over here is the profit, so let's find that out. And so we get 1,300. P of 10 comma 15 is equal to 1,300. Okay, so the revenue collected was 2,750, but the profit realized is 1,300. This is when we produce 10 units, right? X, oh, let's zoom out a little bit. Okay, so when we have P price for the 10-speed bike, and of course, if we wanted to find the price, we would input 10, 15 into this equation. 10, 15. Let's just go ahead and do that. So P equal to 230 minus 9 times X, which is, let's say it's 10. Put that there, plus blank. So it's going to be 10 for X and 15 for Y. Means that P equals to 230 minus 90 plus 15. 230 minus 90 is equal to 140. So we have a price of 155. Q is equal to 130 plus X, which was 10, minus 4 times 15, which is the Y. So Q is equal to 60. 130 minus 60 is going to be 70, plus 10 makes it 80. Okay, so we have everything we could possibly use. So when we have a weekly production rate of 10 of the 10 speeders, well, let's put these numbers in here. So for this particular situation, we have that the price ends up being 155, and this one ends up being 80. And this is when X equals to 10 and Y equals to 15. So when we're producing a weekly rate of 10 of the 10 speeders and we're selling them at $155 per unit, and we're producing 15 of the 3 speeders and selling them at $80 per unit, then the revenue collected, the total revenue collected, is $2,750. We could also confirm that number by multiplying these values, right? We made 10 units at $155 each. So we can come back over here and confirm that number. It would be 155 times 10. This is the total amount of revenue collected from the 10 speeders, plus 80 times 15. And we get the same value, $2,750. So that's the total revenue collected. On the other hand, there was a cost associated with producing them, and that's what this is right here. So we could also evaluate the cost function at 10, 15. What would that get us? Let's come back over here. That would be C of 10, 15 is equal to 200 plus 80 times 10 plus 30 times 15. Okay, so 80 times 10, that's going to be 800, and 2 makes it 1,000, and this is 450, so this is 1450. 1450. So that's the total cost of producing 10 speeders and 15 3 speeders. So it's the cost of producing them. And of course, this is the total revenue collected. So if we subtract 2750 minus 1450, we get to the profit, which is 1300. Right, so that matches up. Okay, so we're able to find everything, more than what they even asked. We know the price for the 10 speeders is going to be $155. The price for the 3 speeders is $80. When we are selling 10 of the 10 speeders and 15 of the 3 speeders per week, we are collecting a total of $2,750 in revenue. The cost function can give us how much it costs us to produce those 25 bicycles. $1,450 is that price. and then we can use that to find the profit, which is 1,300. Okay, so this section shouldn't be hard. It really is just learning to get comfortable with equations that have more variables. But there really shouldn't be anything too tricky in this section, except maybe the graphing, 3D graphing might be new to a lot of people, but there really isn't anything too complicated in this section. All right, so please try the homework out and let me know if you have any problems.